Okay, in this video what we're going to do is we're going to solve some systems by graphing. This should be a follow-up to 7.1 notes. So let's get to it. You're going to be given a system which is going to be contained with two linear equations. You have to decide what form they're in to decide which way you actually want to graph them. So looking at these, I'm going to go ahead and label these so you can see the difference between the two. Looking at example 1, it's in it's in standard form, meaning that I'm probably going to solve this using the intercepts method. Okay, which is sometimes referred to as the cover-up method. I like to write this on the side. It reminds me that I'm finding a couple of points, particularly if I put a 0 in for the y-intercept, I'm finding for an x-coordinate, I'm going to find the y-intercept, so I'm going to find that value and then I get a point on the y-axis. And then if I put again 0 for the y value, I'm going to find a coordinate for the x, and I'm going to get an x-intercept. And I'm going to graph using those 2 points there. So using that idea, I'm going to go ahead and plug 0 in for x first. This whole term is going to turn to 0. So I'm going to get 4y equals 12, which is pretty easy to solve by dividing 4 by both sides. I'm going to find out that y is equal to 3. So my first coordinate point is 0, 3. The second point I'm going to do is by plugging 0 into this term. So that's going to result, and I'm just going to shorten this up a little bit, into 3x equals 12, because this whole term turns to 0. So then I can solve this pretty easily by dividing both sides by 3 and finding out that that's going to be 4. So I get 2 points that I can graph with. I don't need slope and a bunch of points. I just need 2. So for this point, I'm going to go to 0, 3, which is left and right none, up 3. There's my y-intercept. And now I'm going to go 4 over and up none and graph my other point. This point, I should grab a ruler, but we'll freehand it and see how we do. And there's a pretty decent line to represent equation 1. So for equation 2 then, I'm going to do that in red. This one's in slope-intercept form. So the two pieces I need for 2, the two pieces of information I need to grab is 1, the y-intercept. So in this case it'll look like 0, 3 or the point 0, 3, because that's what that represents. And my slope, which will be negative 3/4, right? Just the coefficient of x. So I'm going to go to 0, 3, which is going to place it right there. And then I'm going to go down 3, 1, 2, 3, and over 4. 1, 2, 3, 4. And you're like, wait a minute, what's happening here? I'm going to repeat that process. 1, 2, 3, 1, 2, 3, 4. And you'll find that all of your points, and I'm going to go the other way, up 1, 2, 3, 1, 2, 3, and over to the left 4. What I'm going to find is that all of my points for the line that I'm graphing here for line 2 seem to fall on the line that I've already created. This happens to be one of our other possible scenarios. Remember that if two lines intersect, that's usually a single solution, which we call consistent and independent, right, by the previous video. This one happens to be consistent, which represents that it has a solution, but it's going to be dependent because at every x value that we plug in, it represents a solution because it intersects. It's the same line, it's overlapping. So this is consistent and dependent. So you would say that this is a consistent and dependent solution with basically an infinite number of solutions available. All right, let's look at another problem here. So in this example, you can see that we have two equations again, two linear functions. One in this point is, the first one is in point slope form, where the second one is in slope intercept form. So to graph from point slope form, we could change the form, but the easiest way is to pull out the point. So let's recognize where it is. Remember that point slope form looks like this. And the x-coordinate here, or x1, represents the x-coordinate of our point, and this y1 represents the y-coordinate of our point. So we're going to go ahead and pull this out. Since it's a -1, that means it's going to come out as a 1, right, because it's negative originally in the problem. And again, this is a -5, so when it comes out, it will also be a +5. So there's our point. And then the slope's pretty easy to recognize here because it's the m. So my slope for this one is 3, or better said, 3 over 1. So let's graph the first point, or the first line. I'm going to go to 1 and I'm going to go to 5. Put my point, any point, notice it's not a y-intercept like the other one that we just did. And I'm going to do my slope from there, which is up 3, 1, 2, 3, and over 1. I'm going to repeat that as the opposite version of that, or -3 over -1. So I'm going to go down 3, 1, 2, 3, and left 1. Repeat that again, 1, 2, 3, and left 1. That should be enough to sketch a pretty good line in there. So I'm going to have a line that represents the first one on our system, which would look like that. Our second line, I'm going to use slope-intercept form for, so I can pull off the y-intercept, maybe making sure to take the negative, so it'll be the point negative, or 0, negative 2. And my slope here is 3, or better said is 3 over 1. So I'm going to go to 0, negative 2. That would be this point here, and then I'm going to go up 3, but you'll notice that the slope is identical to the other line. And what that tells me is that it's a parallel slope. And since I have a different y-intercept, you can see that the y-intercept would be here for the red line, or line 1, and here for the other line. It means if the slopes are the same, that I'm never going to get closer or farther from that first line, meaning that these are parallel, or there is no solution to this system. And what we like to say is that the solution to the system is inconsistent. Okay, there's 2 examples for you showing both a consistent dependent and an inconsistent system. Good luck, we'll see you in class.